Okay, maybe we can make a start. So this is our time temperature transformation diagram, and we have already discussed martensite. We've discussed low bainite and upper bainite, and also how to use the information that we have discovered so far in designing new steels. So I'm going to move up in temperature again, but still remain with the displacive transformations and talk about Widmanstaetten ferrite. Okay, so how does Widmanstaetten ferrite form? What are the consequences on the structure and properties? Now, I explained to you several times now that supposing we have austenite with two different kinds of atoms, we can transform it into a different crystal structure by two essential methods. The first involves a homogeneous deformation of the crystal structure into a new shape, and as a consequence we get a macroscopic shape change, which has the form of an invariant plane strain with a large shear component, and there is an atomic correspondence between the parent and the product phases because the neighboring atoms are not actually altered in their relative positions. Okay? On the other hand, when we have reconstructive transformation, we achieve the change in the crystal structure by breaking all the bonds and rearranging the atoms so that there isn't a large amount of strain energy created. And we can imagine this transformation to occur in two steps. It doesn't actually happen like that, but you can imagine it happening in two steps. That first we have a displacive transformation, you cut this part off and bring it over here, and therefore you have diffusion, which eliminates any shape deformation. Okay? So these are the two mechanisms, and I'm going to present to you these mechanisms in a slightly more entertaining manner. This transformation is an extremely disciplined transformation, whereas here the atoms move in a random manner. So supposing we imagine the displacive transformation first, and you have a queue of soldiers who are waiting at a stop where the military transport is going to take them to, military service or whatever, and they have certain names. When they board the bus, they board in a highly disciplined manner. So their near neighbors are still the same, irrespective of whether they like each other or not. They have to sit where they're told to sit. So there's a lot of strain energy there. So this is called a military transformation, where you have a highly disciplined movement of atoms. Now imagine the second scenario, where we have a queue of civilians here waiting at a bus stop, and the bus arrives and they don't care. They will rush on the bus in an uncoordinated manner, and they will go and sit next to people that they want to sit, even though the positions of the people in the queue are different. So we've lost all correspondence between the queue and the positions in the bus. And in that process, we've minimized strain energy. But, of course, this requires a chaotic movement of atoms, which means that it must happen at a sufficiently high temperature to allow atoms to move about at random. And there is a third kind of transformation. Okay, so first we had the military transformation, and then we have the civilian transformation. And in all countries, in addition to the military and the civilians, we have paramilitary. Yeah, have you heard that term before? Paramilitary is not quite soldiers, and they're not quite civilians. They are usually used for internal order, and they are less disciplined than soldiers. Okay, so I'll illustrate what I mean. So imagine that we have a queue again here, and there are large atoms and small atoms, right? Now these large atoms will move in a disciplined manner, but the small ones will go and occupy wherever they like to occupy. So the small atoms are diffusing during transformation, but the large atoms are displaced. So the change in crystal structure is achieved by a displacive mechanism, but small atoms, for example carbon atoms which are in the interstices, are able to partition between the parent and the product phases during transformation. So that's called a paramilitary transformation, and in technical language that's called a para-equilibrium transformation. So let me just write down what what I mean. So para-equilibrium means that the change in crystal structure is achieved by a displacive transformation. Okay. So change in crystal structure is achieved by displacive transformation. In other words, there will be no change in the iron to manganese atom ratio anywhere between the austenite and ferrite. The ratio of the manganese atoms to iron atoms, both of which are large atoms, remains constant during transformation. So there is no change in X to iron atom ratio, where X is a substitutional solute However, subject to that constraint, the carbon atoms will be fused during transformation and end up in the phase where they prefer to be. In the case of steels, the carbon will partition into steels. Okay. However, fast diffusing atoms such as carbon partition during transformation. Exactly analogous to the queue of small and large atoms boarding a bus. So this transformation will have all the characteristics of a displacive transformation. That means we will see a large shape deformation with a shear, and there will be a lot of strain energy, and because of that you will have a plate shape. Okay? And the reason why we are getting this kind of a mechanism is because we've changed the temperature to a higher temperature, where the carbon atoms are now too mobile to be captured as the interface moves. So let me now show you the list of characteristics of Widmanstaetten ferrite. Okay. Just like we listed the characteristics, observed characteristics of bainite and martensite, I'm going to go through what we mean by Widmanstaetten ferrite. Notice also that because carbon partitions during transformation, that means the ferrite never has an excess concentration of carbon, this is not restricted to forming below the T0 temperature. It can even form above the T0 temperature. The T0 temperature only defines the point where diffusionless transformation becomes possible. Okay? So Widmanstaetten ferrite formation is not restricted by the T0 curve. It can form at higher than the T0 temperature. Okay, so this is what Widmanstaetten ferrite looks like. This is my austenite grain structure, and we get these characteristic plates. Okay, so these are not carbides, by the way. This is just a shading, right? These are characteristically triangular shaped sections, and we call that a wedge, W-E-D-G-E. And when they grow directly from the austenite grain surfaces, they are called primary Widmanstaetten ferrite. And supposing we already have some ferrite at the grain boundary, and the plates grow from that ferrite, then they are called secondary Widmanstaetten ferrite. That's just definitions. There is no fundamental difference between this and this. But the shape here is somewhat different from what we get in martensite and bainite, that it is in the form of a wedge-shaped object. Okay? So we need to explain all that. Now obviously I've drawn this structure so that it looks very coarse, because if an austenite grain size is about 30-40 micrometers, then here we have plates which are growing roughly the size of the austenite grains. And furthermore, when we look at this in an optical microscope in a partially transformed condition, that means that we haven't transformed all of the austenite. This is martensite. This doesn't etch dark, right? Do you remember when you saw the optical micrographs of bainite? They were really dark compared with the martensite. This does not etch dark. What does that mean? Yeah, remember we explained that bainite etches dark because it has a lot of structure inside what we see optically, right? This does not. This is clean. It will appear white in your optical micrographs. Okay? So you can distinguish this easily from bainite from the way it etches with respect to untempered martensite. Okay? And you can see also the shapes of the plates here. Okay, so there's a clue from the optical microscopy that there isn't significant structure inside what we observe as plates of Widmanstaetten ferrite. Obviously, if the change in crystal structure is achieved by a displacing mechanism, then we should be able to pick up a shape deformation. And what are the methods we have used for characterizing the shape deformation? Supposing I wanted to show that a transformation product produces a shear, what experimental technique have we used so far? With martensite, how did we prove that there's a shape change experimentally? So if somebody shows you the structure of X80 line pipe and says, what is this? Yeah? You won't be able to tell just by looking at it. You've got to do a whole series of experiments to show whether there's a shape change, etc. How would you do that? Okay, so let me give you a clue. So we had the interference micrograph. Do you remember the nice, beautiful colors showing the martensite plates? Yeah, do you remember that or not? Let me pull it out. So we polish a sample completely flat, and then we allow it, a sample of austenite completely flat, mirror finish, allow it to transform into martensite, then the surface is tilted, everywhere you have martensite, and interference microscopy relies on height differences. Okay? So this is not an etched sample, this is an optical interference micrograph. So you could do an experiment like that. But your structure has to be optically resolvable because this is about 50 micrometers. In the case of bainite, we can't do that, right? So what technique would you use? What technique did we use to show the shape deformation? Yeah, you said something? Yeah. So atomic force microscopy, which basically is a high resolution method of looking at surface topology, and scanning tunneling microscopy is similar. They just use different kinds of signals from the sort of not indenter, but the device which goes over the surface to record the topology. So here the scale is 1 micrometer and the vertical scale is 200 nanometers. Right, so we've seen that Widmanstaetten ferrite plates are coarse, so we don't need to use atomic force microscopy to characterize this. we can use optical microscopy, and there are two methods illustrated here. This is a different kind of interference microscopy. It's called Tolansky interference microscopy. You have all of these techniques are available here, where you look at the displacement of fringes which are formed by interference, and from that you can measure the tilting, the shear, etc. And a much simpler method is when you prepare your metallographic specimen, there will always be scratches, right? And look, the scratches are deflected wherever you see the plate of Widmanstaetten ferrite, and from that deflection of the scratch you can work out the shear deformation. If you look at a picture of the San Andreas Fault in California, yeah, from a big height, you can see that plantations of oranges, yeah, were displaced when the fault slipped. So that's exactly the same. This is the deflection of a scratch by a phase transformation. The San Andreas Fault is on a much, much bigger scale. Okay? Right. So we have here a shape deformation, which is an invariant plane strain. But unlike bainite, both of these are plates. Okay? On both sides of those fringes, which are displaced in opposite directions, are plates of Widmanstaetten ferrite. So what's happening is that if we form a single plate at a time, as illustrated in A, then the strain energy is just too great to allow the Widmanstaetten ferrite to form at high temperatures close to the A3 phase boundary. Yeah? Because we've raised the temperature, the driving force for transformation decreases, and you cannot easily sustain such a large strain energy due to the shape deformation. So instead of isolated plates forming, you get the situation illustrated in B, where you have two plates forming together in such a way that they cancel out each other's shape deformation, and that results in a dramatic reduction of strain energy to just about 50 joules per mole, compared with, say, 600 joules per mole in the case of martensite. Right? So it's very clever. You've got two plates growing together in such a way that they cancel out each other's shape deformation. Not completely, because they don't have the same plane on which they form, but they cancel out each other's shape deformation. The consequence of this is that you have to nucleate two plates simultaneously with the correct shape changes, right? The probability of nucleation therefore decreases, and therefore you end up with a very coarse microstructure. So Widmanstaetten ferrite plates are not good for mechanical properties. It's much coarser than what we get with bainite, because the chances of nucleating two appropriate plates simultaneously is of course less than isolated nucleation events, right? So from the growth point of view, Widmanstaetten ferrite can grow very close to the A3 temperature, well above T0, because the effect of the strain energy is dramatically reduced by the simultaneous growth of plates. That also explains the shape, because this plane is different from this plane. Yeah? They're the crystallographic variants, that means the same indices but arranged in a different way. So clearly there will be a finite angle between these two planes, and that is the reason why you get a wedge shape. Yeah? You cannot have two plates with exactly the same shape deformation but different planes. Yeah? It's because there are different shape deformations here and here that the habit planes are also different, and we predict that there should be a single boundary when we look at this in a transmission electron microscope. Right? Everyone happy with that? And indeed that's exactly what you see. This is, you can see the scale here. It's a coarse plate. We were talking about quarter micrometer for bainite and so forth. Here is a small low angle boundary between the two plates which form an optically single plate of Widmanstaetten ferrite. Okay. Right. Now, of course, if this forms by para-equilibrium transformation, that means carbon must diffuse during transformation, then the growth rate of these plates will not be fast, because the carbon has to get out of the way in order for the plate to grow. So I'm now going to go through the theory for the growth rate of these plates. Okay? The diffusion-controlled, carbon diffusion-controlled growth rate of Widmanstaetten ferrite plates. And the theory that I'm going to teach you is simplified. So it's not perfectly accurate. Accurate theory is available, but it tells you absolutely everything that you need to know about the nature of the growth process. Okay? There's no point in doing things in a more complicated way than is necessary in a lecture. So I'm going to make approximations that, for example, the concentration gradient is constant at the interface rather than some kind of an error function and so forth. Yep. Okay, so the first thing is the shape of Widmanstaetten ferrite. Well, the wedge shape is approximately the same as what we call a parabolic cylinder. So if I take a parabola and I push it in this direction, then that generates a plate shape. Right? So if I sketch that, the shape of a plate is that of a parabolic cylinder. That means it's like that. Yeah? Can you see that? It's like a parabola being pushed through space. And there is a characteristic radius at the tip. Okay? So the tip radius, oops, let me just write that a bit more clearly. So that is the model of a plate of Widmanstaetten ferrite. Everyone clear about that? And this distance here we will call L. Now, as the plate grows, carbon is being partitioned into the austenite, and this is the free energy, and the concentration, and we have the free energy curves of alpha and of gamma. And if I draw a common tangent to these curves, then that gives me the equilibrium composition of ferrite and of austenite, which I will label as C gamma alpha and C alpha gamma, where C alpha gamma is the composition, the equilibrium composition of ferrite, is the composition of alpha in equilibrium with gamma, and C gamma alpha similarly is the composition of austenite, which is in equilibrium with ferrite. And somewhere in between these values we have the average composition of our steel, which I will call C bar. Okay? So C bar is the average concentration in the steel. So just to summarize, when austenite is in contact with ferrite, the maximum carbon concentration it can tolerate is given by this value, okay, which is the A three-phase boundary, and the composition of the ferrite is given by this value. So if I now draw the concentration profile at the moving interface, then it will look something like this. So this is distance, which we will call Z, and this is concentration. Then the composition far away from the interface is C bar. This is our ferrite, and this is austenite. The thickness of the length of the ferrite we will write as Z star. Okay, so Z star is the position of the alpha gamma interface of alpha gamma interface. This distance here is the diffusion distance. Now, if I did this properly, then the diffusion distance would extend much further because it's like an error function. Okay? But this is a very good approximation to take just a constant gradient. Now, I've got to derive an equation for the growth rate. So I'm going to replot this concentration profile after the interface has advanced a little bit. So this is again Z and C, and let's say this is the initial position, and after a certain time it advances like this. That is the amount of carbon that has been pushed as the interface advances, and if I take this advance as delta Z and I have a velocity, then that is the amount of carbon that has been pushed ahead of the interface. Yeah, because the ferrite has this concentration here. Is everyone happy with that? Okay, so actually I need to go back. If I write the velocity of the interface, velocity is equal to dz star by dt, where t is the time. Then the velocity multiplied by this value here, which is C gamma alpha, and this is C alpha gamma. So C gamma alpha minus C alpha gamma is the rate at which solute is being pushed ahead of the interface. Yeah, the rate at which solute is being pushed ahead of the interface. Is everybody happy with that? dz by dt, dz star by dt, multiplied by how much solute we've got to get rid of for ferrite to grow. Yeah? Now, if I push carbon into the austenite, then this concentration C gamma alpha will increase, right? But that's not allowed. So we've got to carry away by diffusion the carbon from ahead of the interface at the same rate at which it is being partitioned. So the rate at which we carry away the carbon by diffusion is equal to the diffusion coefficient times the gradient of concentration, which is C gamma alpha minus C bar divided by the diffusion distance ZD. Yeah, that is Fick's first law of diffusion. Yeah, we have the concentration gradient times the diffusion coefficient. So C gamma alpha minus C bar is the difference in concentration, and divide by the distance, that gives you the flux away from the interface. If those two are different, then C gamma alpha will change, which is not allowed. Okay? Is everybody happy with that? Okay. Right, so I'm going to write that equation out again, that the velocity, so this term is dz star by dt multiplied by C gamma alpha minus C alpha gamma must be equal to the flux away from the interface if we are going to maintain the concentration at the interface constant. Must be equal to D into C gamma alpha minus C bar divided by ZD. Very simple. You know, the rate at which solute is partitioned must be the rate at which it diffuses away from the interface if we are to maintain the equilibrium at the interface. Right? Everyone happy with that? Right. I'm now going to say that the diffusion distance ZD is the same as the tip radius R. Okay? So let us assume that ZD is equal to R, because as this plate advances, we are leaving solute behind, okay, and we are advancing into fresh austenite. Yeah, so the tip of the plate is always advancing into fresh austenite, so there's no reason for carbon to build up ahead of the interface apart from a diffusion distance. So we'll approximate the diffusion distance as being the tip radius R. So if I now rearrange this equation, I get the velocity is equal to D times C gamma alpha minus C bar divided by C gamma alpha minus C alpha gamma into 1 upon the tip radius. So we don't actually have an answer for velocity, right? We have the velocity as a function of the radius. And this is a very common problem in phase transformations, that we don't get a velocity, but we get the velocity as a function of some dimension. So if I plot the velocity versus the radius, then I will get a curve which looks like this, where this is the radius and this is the velocity. As the radius goes to 0, the velocity goes to infinity. So this doesn't really make sense. You know, first of all, I don't know which velocity to pick, and secondly, I can't really have a plate of Widmanstaetten ferrite which is infinitely thin. It would grow infinitely fast, but it doesn't make sense. Yeah. So we are losing. We've got something missing from the theory, and the something missing is that we have to account for interfacial area which is created as the plate thickens. Yeah? So if I look at that cylinder at the tip, we can work out the cost of creating interface as the plate thickens. Okay? So we need to account for, for creation of interface. And the interfacial energy is sigma joules per meter squared. So sigma equal to interfacial energy per unit area. So the area of a cylinder, the cylinder is this cylinder at the tip extending into the board. Yeah. The area of the cylinder, A, is area of cylinder is simply equal to pi into the radius, 2 pi r into the radius, 2 pi r times the length, L, so that dA by dr or rather dA is equal to 2 pi L into dr, and the number of atoms in the cylinder, N is the number of atoms cylinder is equal to pi r squared into L divided by omega, where omega is the volume per atom. Per atom. So I can write dN is equal to 2 pi L into R over omega dr. Oops. Okay. 2 pi Lr into divided by omega multiplied by dr. Yeah, is everybody happy with that? So, the change in area as I add atoms to the plate is given by dividing this one here by this one, which is 2 pi L will disappear. We have 1, let me see, it will be R divided by omega. R which is the tip radius divided by omega. Okay. So the rate of change of surface area as I add atoms is R divided by omega, right? No? Have I made a mistake? The other way around, omega upon R. Okay. elementary mathematics is not my strength. Okay. So it's omega upon r, because we are dividing dA by dN. Yep. Okay, so remember that the rate of change of area with the number of atoms that we add is given by omega upon r. So we are creating that interface as the Widmanstaetten ferrite thickens. Okay, so the energy cost of that is just interfacial area per energy per unit area multiplied by that term. So the energy cost is sigma into omega divided by r, where sigma is just our interfacial energy per unit area. G is the free energy per atom. And I have my free energy curve for austenite and for ferrite. And the effect of this term is to raise the free energy curve of ferrite to a different value, where this difference here is given by sigma omega upon r. So which means that equilibrium at the interface will change, because if I now draw the common tangents, they will have different values. Yeah. So this is the common tangent when the radius is infinite and it changes when the radius is finite. Okay. So here we had the concentration C gamma alpha, and here we have a different concentration C gamma alpha for a finite tip radius r. So we are consuming some energy in creating an interface. And if the driving force for transformation is delta G, okay, when the interface radius is very large, okay, delta G is the driving force for transformation, then delta G with R is the driving force for transformation when we have a finite tip radius. Okay? R is equal to delta G minus sigma omega divided by R. So we are removing some of the driving force to create interfaces. Is everybody happy with that so far? Now, at some point, the radius will become so small that all of the driving force is used up in creating interface, and the growth rate will be 0. Yeah? So if I set this equation to 0, so at a critical radius, RC, delta GR is equal to 0. In other words, delta G is equal to sigma omega over the critical radius. So I can rewrite this equation here as delta GR is equal to sigma omega into 1 upon RC minus 1 upon R. Yeah, the first term just substitutes for delta G. here I'm just substituting for delta G in terms of the critical radius at which the growth becomes 0. And this is the term coming from here. Yeah, everyone happy with that? So velocity is proportional to driving force. So what we are saying is that when we have a radius which is not infinite, we will have a reduction in driving force by this bracket here. Okay? So if I go back to my velocity equation, which I wrote earlier, here, and I simply multiply it by that term which reduces the driving force by a factor which depends on the tip radius, then I will have a more reasonable theory. So I'll write that out again. So since velocity is proportional to delta GR, we can write the velocity is equal to the diffusion coefficient times C gamma alpha minus C bar divided by C gamma alpha minus C alpha gamma into 1 upon the tip radius. This is the previous term, and multiply it by 1 upon RC minus 1 upon R. So that's a much more reasonable treatment of the growth of Widmanstaetten ferrite. If I now plot this R and velocity, then I get a classic curve, which is not just true for Widmanstaetten ferrite, but also for dendritic growth, for example, and many other transformations. So here we have a velocity of 0 when the tip radius is the critical radius, RC. And this is the maximum velocity. And that maximum velocity, Vmax, is when the tip radius is equal to 2RC. So how would you prove that? Yeah. We differentiate this equation and find the maximum and prove it for yourself, all right? That the maximum occurs when the radius is equal to 2RC. Now, I don't have any justification, fundamental justification for doing this, but I feel happy to say that the plates will grow at the fastest rate possible, right? So I cannot theoretically justify it, but let's assume that plates grow at the maximum velocity. In other words, they choose a radius which will give the maximum growth velocity. Okay? Previously we had no solution at all. And I'd like you to note that this is an important equation because it contains terms from the phase diagram, okay, the equilibrium concentrations, contains your steel position C bar. It contains the interfacial energy per unit area because the critical radius depends on the interfacial energy, and you've got a diffusion coefficient. So there's an awful lot of theory in here to allow you to change the parameters for Widmanstaetten ferrite growth when you're designing a steel. Now, when you measure the growth rate of Widmanstaetten ferrite and you compare against calculations, so this is the calculated rate and this is the measured. So this rate is the maximum lengthening rate, right? At the peak of that curve that I showed you. When you compare, you get pretty good correlation. The calculated rate here is a little smaller than the measured rate. So that's why I was saying I feel happy to choose the maximum rate, because even when I take the maximum rate, it's slightly smaller than the actual rate, and that's obvious why. You know, there are many approximations that we've made. For example, taking a parabolic cylinder as opposed to a wedge shape, and so forth and so on. But you can pretty well calculate within 5 micrometers a second, you can calculate the growth rate as a function of steel composition for Widmanstaetten ferrite. Right, let me summarize then. This is what we mean by Widmanstaetten ferrite, that the mechanism of transformation is displacive. That means you expect a plate shape, you expect an invariant plane strain shape deformation, but with the additional feature that 2 plates grow at the same time, so that it can happen at a higher temperature. But there is absolutely no doubt that it can form above the T0 temperature, and therefore there must be partitioning of carbon during the growth of the plates. And indeed, when you measure the growth rate, it's consistent with carbon diffusion control growth. This is important because when you have to have pairs of plates growing together, the probability of nucleating 2 plates at the same time in the same location and with the appropriate shape deformations is small. And therefore, the structure will always be coarse, and it is bad for your mechanical properties when structures are coarse. Okay. I'm going to ask you if you have any questions. I know nobody will ask any questions, okay? But if you do have questions, feel free to ask questions anytime. All right, you can send me an email if you want. Okay? Okay, that's all for today. Thank you.